Right now, as you watch this, something invisible is passing through your body. Not a thought, not air, not light. Antimatter. Tiny particles of it, the rarest, most exotic substance in the known universe, are colliding with the atoms inside you at this very moment. They have been doing this your entire life. They did it while you slept last night. They did it the moment you were born. They did it long before humans walked this planet. And for most of history, we had no idea. We didn't know where these particles were coming from. We didn't know what was making them. We pointed our telescopes at every corner of the sky and found nothing that could explain it. For decades, some physicists quietly wondered if the answer was something we had never encountered before, something that would rewrite our understanding of matter itself. The answer, when it finally came, was somehow more astonishing than anything they had imagined. It was a dead star. A dead star, 800 light-years away, spinning 4 times every second, trailing ghostly X-ray tails across 3 trillion kilometers of space. And it had been bombarding our planet with antimatter for longer than our species has existed. Silently, invisibly, relentlessly. And that star, that extraordinary, violent, beautiful, almost incomprehensible object, is just one of a kind. Just one example of what may be the strangest category of object in the entire observable universe. Tonight, we are going to follow the evidence into the deep unknown. We are going to cross into a realm where matter behaves in ways that have no parallel in ordinary experience, where a single teaspoon of material outweighs every human being who has ever lived, where the surface of an object the size of a city generates gravity so extreme that if you fell from just 1 meter above it, you would hit the ground moving at 1,500 kilometers per second. We are going to talk about neutron stars, and I promise you, by the time we are done, you will never look at the night sky the same way again. Take a breath, get comfortable, let your mind open, because the universe is about to show you something extraordinary. Let's begin somewhere quiet, somewhere that feels, at first, almost ordinary. Imagine you are standing outside on a clear night, far from any city, far from any artificial light. The sky above you is the deepest black you have ever seen, and it is absolutely filled with stars. Thousands of them, tens of thousands. So many that the individual points of light begin to blur into a soft, luminous band stretching from one horizon to the other. The Milky Way, our galaxy, seen from the inside. Now, somewhere in that band of light, in a region of the sky we call the Gemini constellation, there is something you cannot see. Not because it's too small, not because it's too dim, but because it is operating at a frequency your eyes were never built to detect. It is pulsing with gamma radiation and X-rays, sending waves of high-energy light across the 800 light-years between us with a rhythm as steady as a heartbeat, once every 0.237 seconds, 4 times every second. It has been doing this since long before the Roman Empire fell, long before the pyramids were built, long before the first modern humans crossed out of Africa. We named it Geminga. The name is a small, quiet piece of poetry. It combines the constellation where it lives with the type of radiation it emits. But in the Milanese dialect of Italian, it also means something else entirely. It means, it's not there. And for a long time, that is exactly what it seemed like. A source with no visible origin. Radiation arriving from a point in space that appeared, to every instrument we had, to be completely empty. Geminga was first detected in 1972. For nearly 2 decades after that, we had no idea what it was. That is where we begin. But to understand why Geminga is so strange and why it matters so deeply to the story of the antimatter raining down through your body tonight, we first need to understand what neutron stars actually are. Because most people have heard the name, very few people truly feel what these objects mean. So let's take a moment. Let's really sit with this. Every atom in your body, every atom in this planet, in every planet, in every star you have ever looked at, is almost entirely empty space. The nucleus of an atom, where virtually all of its mass is concentrated, is vanishingly small compared to the total size of the atom. If you were to magnify a single hydrogen atom until its nucleus was the size of a marble, the outer edge of the atom's electron cloud would be somewhere around the length of a football field away. That is how much empty space exists inside ordinary matter. That is how hollow everything around you truly is. Now imagine taking all of that empty space away. Imagine taking a star, an entire star, something so massive that its gravity holds a solar system together, and crushing it until every atom is compressed, until the electrons are driven into the protons, until protons and electrons merge under the unimaginable pressure into neutrons. And all of those neutrons are packed together so tightly that there is no space left between them. What you have left is a neutron star, an object that contains more mass than our Sun, sometimes 1.5 times more, sometimes twice as much, sometimes approaching 3 times the mass of an entire star, compressed into a sphere roughly 20 to 30 kilometers across, the size of a city, the mass of a star, no empty space whatsoever. A single teaspoon of neutron star material would weigh approximately 4 billion tons, not 4 billion kilograms, 4 billion tons, on Earth, the weight of 10,000 Empire State Buildings balanced on a spoon. The gravity at the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel right now. If you were somehow placed 1 meter above the surface of a neutron star and released, you would reach the surface in a fraction of a millisecond, hitting it at approximately 1,500 kilometers per second. You would not survive. You would not even remain recognizable as matter. You would be compressed flat against the surface to an atomic scale, your atoms crushed into the same neutron degenerate material that makes up the star itself. The neutron star would not notice. Its surface, already subjected to gravity of that magnitude, would register your arrival the way a mountain registers a falling raindrop. But here is what is truly astonishing about neutron stars. It is not the gravity. It is not the density. It is not even the violence of their creation. It is the fact that they spin. When a massive star collapses to form a neutron star, something called conservation of angular momentum takes over. The same principle that causes a spinning ice skater to accelerate when they pull their arms inward. As the collapsing star's outer layers fall inward and the core contracts from something the size of the Sun to something the size of a city in a matter of seconds, its rotational speed increases by an almost incomprehensible factor. A star that was rotating once every few weeks suddenly becomes an object spinning dozens, hundreds, sometimes thousands of times per second. And because the neutron star is so incredibly dense, and because the physics of its interior generate magnetic fields of almost unimaginable strength, fields that can be trillions of times stronger than Earth's magnetic field, something extraordinary happens at its poles. Electrons are torn from the surface and hurled along the magnetic field lines at relativistic speeds. As they accelerate, they emit photons. Those photons interact with the quantum field around them, creating pairs of electrons and their antimatter counterparts, positrons. Those pairs emit more photons. Those photons create more pairs. The cascade grows exponentially, producing an intense, highly focused beam of radiation that pours out of each magnetic pole like light from a lighthouse. And because the magnetic poles of a neutron star are almost never perfectly aligned with its rotation axis, just as Earth's magnetic north pole is offset from its geographic north pole, those beams sweep around as the star spins. If one of those beams happens to sweep across Earth, we see a pulse of radiation. A bright, sharp flash, repeating over and over with the precision of a clock. We call these objects pulsars, and they are, without question, the most accurate timekeepers in the known universe. A pulsar does not drift. A pulsar does not need to be wound or reset. A pulsar does not lose seconds over years. The best millisecond pulsars, the fastest spinning ones, completing hundreds of rotations every second, maintain their timing with a precision that rivals or exceeds the finest atomic clocks we have ever built on Earth. We can measure the arrival of their pulses from thousands of light years away and predict, with extraordinary accuracy, exactly when the next pulse will arrive. They are the clocks of the cosmos. And yet, and this is where the story begins to take a turn that no one anticipated, some of them are doing something they should not be able to do, something that by every model we have should be impossible. Let's talk about what happens when a pulsar grows old. Every time a pulsar emits radiation, it loses energy. That energy has to come from somewhere, and it comes from the rotation of the star. Every pulse slows the pulsar down, very slightly, very gradually. Over time, over thousands, millions, sometimes billions of years, a pulsar spins more and more slowly. The lighthouse sweeps more and more slowly. The lighthouse sweeps more and more slowly. The pulses arrive further and further apart. Eventually, the star slows to the point where it can no longer generate the conditions required for the pair production cascade at its poles. The electric field at the surface drops below the threshold needed to tear electrons from the surface and hurl them along the magnetic field lines. The cascade stops. The beam of radiation dies. The pulsar goes dark. We call this region of perimeter space, this graveyard where pulsars go to stop shining, the Death Valley. On a graph that plots neutron stars by their rotation period on one axis and their rate of spin down on the other, the Death Valley appears as a broad band. Any pulsar whose properties place it within or below that band should not be detectable. It should be dark, silent, invisible. And for a long time, we assumed that every pulsar we would ever detect would lie safely above that line. Then, in 2022, astronomers using a radio telescope array in Western Australia were reviewing archival data, records of old observations, years of stored signals, and they found something. A signal. Arriving from a fixed point in the sky, returning again and again with remarkable regularity. Once every 21 minutes and 58 seconds. They traced it backward through the data and found it had been arriving since at least 1988. 35 years of this signal, hiding in archives, waiting to be found. And when they calculated how much the source had slowed down over those 35 years, they found something that stopped them in their tracks. The rotation period had not measurably changed. In 35 years of observation, the rotation of this object had slowed by no more than 0.28 milliseconds. That is not a typo. That is 0.28 thousandths of a second over 35 years. The stability of this signal is comparable to the best pulsars we know, objects that we use precisely because of how reliable they are. But here is the problem. Here is the thing that made the astronomers stare at their data in silence for a long moment before they began to speak again. This object should not be able to shine. Its rotation period is 1,318 seconds, more than 20 minutes per rotation. The typical pulsar spins between 10 times per second and once per second. This object is rotating over 1,000 times more slowly than that. And when you plot it on the Death Valley graph, it falls not just within the Death Valley, but well below the lowest line. It is in territory so deep in the Death Valley that no known physics can explain how it is generating any detectable radiation at all. And yet, there it is, a signal polarized in the way that only neutron star emission is polarized, showing the characteristic 90-degree flip that is a hallmark of the cascade process at a neutron star's poles, arriving from a source 18,000 light-years away in the galactic plane, stable beyond anything a conventional dead star should be capable of. We named it GPM J1839-10, and we do not know what it is. The astronomers who discovered it explored every possibility they could construct. Could it be a magnetar, a neutron star with an extraordinarily powerful magnetic field, capable of producing starquakes that release enough energy to briefly relight the dead beacon? The most powerful magnetar outburst ever detected released so much energy that had it occurred 10 light-years away, it would have caused a mass extinction on Earth. If anything could wake the dead, it would be that. But magnetar outbursts do not last 35 years. They are cataclysmic events that dissipate within months. And GPM J1839-10 produces no X-ray emission, which a magnetar event should. So, not a magnetar. Could it be a white dwarf? The remnant of a smaller star? One that did not collapse all the way to neutron degeneracy, with an unusually strong magnetic field producing radio emission? White dwarfs are larger and less dense than neutron stars, and they would not be subject to the same Death Valley constraints. But the one known radio-pulsing white dwarf produces signals roughly 1,000 times weaker than this source. And to produce the luminosity we observe, a white dwarf would require a magnetic field stronger than any ever detected on one of its kind. So, probably not a white dwarf either. Could it be something we have never seen before? That is not a rhetorical question. That is the actual current scientific status of GPM J1839-10. It is something we have not yet been able to classify. Something that does not fit our models. Something that is, right now, pulsing away in the galactic plane, sending its signal across 18,000 light-years to arrive in our radio telescopes once every 22 minutes. And we do not know what it is, but here is what the astronomers do know, and this is both humbling and thrilling. The ease with which they found this signal in archival data suggests that many more objects like it are out there, already present in data we have collected and simply not yet examined closely enough. There may be dozens of these unknown pulsing objects hiding in our records, waiting to be recognized, each one a potential window into physics we do not yet understand. The universe is telling us something. We are still learning to listen. And if you find yourself wondering, if you find yourself lying awake tonight with the image of that signal in your mind, arriving faithfully every 22 minutes since before you were born, since before your parents were born, since long before anyone alive today first drew breath, wondering what it is, what it means, whether there is something stranger out there than we have words for yet, then you're in good company. You are thinking exactly the way science is supposed to feel. Now, we need to go back to Geminga, because Geminga's story does not end with its discovery as a pulsar, And it does not end with its strange radio silence. It ends, or rather, it opens, into something that reaches all the way to the atoms in your body. By 2005, astronomers had pieced together the full picture. Geminga was confirmed as a pulsar, roughly 350,000 years old, the remnant of a star several times more massive than our Sun that exploded long before humans walked the Earth. It spins 4 times per second. It is racing through space at approximately 210 kilometers per second, heading toward the border between Gemini and Lynx. Behind it, it drags 2 ghostly comet-like tails of superheated plasma and X-ray radiation stretching 3 trillion kilometers across the sky. A wake visible only to our most sensitive space telescopes. What had puzzled astronomers for decades was its apparent silence at radio wavelengths. Every radio telescope pointed at it found nothing. And yet, its gamma-ray and X-ray emission was so powerful that it is one of the brightest gamma-ray sources in our entire galaxy. The explanation, when it came, was almost elegantly simple. Geminga's radio beams exist, but they are not pointing at us. The pulsar is oriented in space such that its radio emission sweeps in a direction that misses Earth entirely. We only receive the gamma-ray emission because that comes from around the equator of the pulsar, in all directions, and that radiation is broad enough to reach us, even though the tight radio beams are not. We were not seeing it because we were not in the right position to receive that particular signal. Not because the signal wasn't there, but then, and this is where it becomes personal, then came 2017 and the high-altitude Water Cherenkov Observatory, a gamma-ray telescope built on a mountain in Mexico that detects gamma rays by capturing the faint blue light they produce when they collide with water. This telescope detected something around Geminga that no one had fully expected. A halo. A vast glowing halo of gamma radiation surrounding the pulsar, extending outward for light years in every direction. The radiation in this halo had energies measured in trillions of electron volts, the sort of energies associated with only one process, the interaction of positrons, antimatter electrons, with starlight, boosting that light up to extreme energies. Geminga was not just spinning quietly in space. Geminga was a positron factory. Its intense magnetic field was tearing particles from its surface, accelerating them to nearly the speed of light, flinging electrons and positrons into the surrounding space. Those positrons were then colliding with photons of starlight and boosting them to gamma-ray energies, creating the halo we detected. But the halo, impressive as it was, appeared at first too small. The positrons producing it didn't seem to have enough energy to travel all the way to Earth, 800 light-years away. So, astronomers thought, interesting, but not directly relevant to what the alpha magnetic spectrometer was detecting aboard the International Space Station, the AMS-2. Let's pause here for a moment and appreciate what this instrument represents. The alpha magnetic spectrometer is a state-of-the-art particle detector, roughly the size of a large car, mounted to the outside of the International Space Station 200 meters above Earth. Since 2011, it has been counting cosmic ray particles, fragments of atoms accelerated to near light speed by violent events in the cosmos, with extraordinary precision. In 2013, the first major results were announced. The AMS-2 had detected more than 400,000 positrons. That was 100 times more positron data than the entire previous history of cosmic ray observation combined. And the numbers were strange. There were far more positrons arriving at Earth than the standard sources, natural radioactivity, cosmic ray interactions, could account for. Something out there was producing positrons in extraordinary quantities. And for years, the most exciting hypothesis was dark matter. Dark matter, the invisible substance that accounts for roughly 27% of all the energy content of the universe. We know it is there because we can see its gravitational effects. Galaxies rotate in ways that only make sense if surrounded by vast halos of invisible mass. But we cannot detect it directly. We cannot see it, touch it, or interact with it in any way we know of, except through gravity. Some models of dark matter predict that dark matter particles should occasionally annihilate each other, producing positrons as a byproduct. The excess positrons detected by AMS-2 were, for a time, one of the most tantalizing hints that we might be indirectly detecting dark matter for the first time. Then came 2019, and a team led by astrophysicist Mattea de Ogna Wilhelmi used a decade of data from the Fermi Large Area Telescope, a space-based gamma-ray observatory that can detect lower energy gamma rays than the ground-based water Cherenkov detectors, to look at Geminga more carefully. What they found changed the picture entirely. When they subtracted every known gamma-ray source from the data, what remained was a glow around Geminga, so vast it was almost startling. Not the compact halo detected earlier, something far, far larger. An oblong region of gamma-ray emission spanning 20 degrees of the sky, comparable to the area covered by the Big Dipper constellation. And at lower energies still, the glow was even larger. An area 40 times the apparent size of the full moon, blazing with gamma radiation we cannot see with our eyes, but which would absolutely dominate the sky if we could. The size of this halo meant something crucial. It meant the positrons producing it had traveled much further from Geminga than previously assumed. Far enough, potentially, to reach Earth. The calculations showed that Geminga alone, this one pulsar 800 light-years away, could potentially account for as much as 20% of the excess positrons detected by AMS-2. Not dark matter, a dead star. A dead star spinning 4 times per second, racing through space at the speed of a bullet, trailing X-ray tails across 3 trillion kilometers, and in its wake, flooding the surrounding parsecs of space with antimatter. Antimatter that reaches Earth, antimatter that passes through you, right now, as you sit or lie, reading or listening to this. The dark matter hypothesis for the positron excess did not survive this discovery. When you can account for the excess with a known, observable source, Occam's razor demands you set aside the exotic explanation. Pulsars, not dark matter, appear to be the most likely source of the antimatter bombarding our planet. But notice what this means. Notice the chain of reasoning that led here. We detected radiation from an unknown source in 1972. We spent 19 years figuring out what it was. We spent more years understanding why it was radio quiet. We discovered it was moving. We found its tails. We confirmed its nebula. We looked at it more carefully with better instruments, and at every step we learned something that changed what we thought we understood. Science is not a destination, it is a direction, and the direction, in the case of neutron stars, keeps pointing toward things stranger than anything we anticipated. Because Geminga is not the only pulsar doing something remarkable. In 2023, an international collaboration of astronomers called NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, announced something that had been building for 15 years. Quiet, patient, incremental work. The kind of science that does not make headlines every week, but accumulates, slowly, into something vast. They had detected the gravitational wave background. Let me explain what that means and why it matters so much. You have perhaps heard of gravitational waves. In 2015, the LIGO detector, two enormous laser interferometers, one in Louisiana and one in Washington state, detected gravitational waves for the first time, generated by two black holes colliding 1.3 billion light-years away. That discovery won the Nobel Prize and confirmed a prediction Einstein had made a century earlier. Gravitational waves are ripples in the fabric of space-time itself, compressions and expansions of the very medium through which everything in the universe moves. LIGO detects high-frequency gravitational waves, the kind produced in the final frantic moments before two massive objects collide when they are orbiting each other hundreds of times per second. These are the dramatic events, the ones that produce the sharp, sweeping chirp of a signal rising rapidly in frequency as the objects spiral together. But there is another kind of gravitational wave, the kind produced not by two objects in their final moments, but by the slow, orbital dance of truly enormous masses. Pairs of supermassive black holes, the kind found at the centers of galaxies, each one containing billions of times the mass of our Sun. These binaries form when galaxies merge, as two galaxies flow into each other over millions of years, their stars rarely colliding because of the vast distances between them, but their gravitational fields drawing everything together. The supermassive black holes at their centers eventually find each other and begin to orbit. Slowly, their orbits shrinking over millions or billions of years until they too eventually collide. The gravitational waves they produce in the meantime are not sharp chirps. They are a continuous, ultra-low frequency hum. So low in frequency that one full oscillation takes not milliseconds, but years, decades. The wavelength of these gravitational waves is measured not in kilometers, but in light years. LIGO cannot hear these waves. Its arms are 4 kilometers long. To detect gravitational waves with wavelengths measured in light years, you would need a detector measured in light years. You would need to build one out of the galaxy itself. That is exactly what nanograv did. Pulsars, as we have discussed, are the most precise natural clocks in the universe. Their pulses arrive with extraordinary regularity, and we can measure that regularity to extraordinary precision. If a gravitational wave passes through the space between us and a pulsar, it will very slightly alter the time it takes for the pulsar's pulses to reach us. The space-time they travel through will be compressed and expanded by the passing wave, and those compressions and expansions will create tiny, systematic variations in pulse arrival times. Tiny. We are talking about nanosecond scale variations, billionths of a second. But pulsars are so stable, and our timing methods are so precise that we can measure these variations. And if a gravitational wave background, a cosmic sea of overlapping waves from countless supermassive black hole binaries throughout the universe, exists, it should produce a specific pattern of correlations between the pulse arrival time variations of different pulses across the sky. Two pulses separated by a certain angle in the sky should show arrival time variations that are correlated in a specific way that depends on that angle, a relationship called the Helling-Downs curve. Nanograv monitored 68 carefully selected pulses for 15 years. Not milliseconds of observation, not months. 15 years of continuous, meticulous timing. Building up a dataset of pulse arrival times measured to nanosecond precision. And when they analyzed the correlations between their pulsars, they found the Helling-Downs curve. The gravitational wave background exists. We have detected it using dead stars as the arms of a galaxy-sized gravitational wave detector. The signal is currently assessed at the 3 sigma level of statistical confidence. meaning, there is roughly a 1 in 1,000 chance it is a statistical fluke. As more data accumulates, that confidence will only grow. But here is what makes this discovery not just scientifically impressive, but almost philosophically staggering. The gravitational wave background is not only produced by supermassive black hole binaries, it is expected to also contain primordial gravitational waves. Waves produced in the first moments of the universe's existence at energies and densities so extreme that they generated ripples in spacetime that have been expanding and redshifting ever since. The cosmic microwave background, the glow of light left over from the Big Bang, the earliest light we can detect, was produced 380,000 years after the universe began. For the first 380,000 years, the universe was opaque to light, a hot plasma through which photons could not travel freely. We cannot see further back than that wall of light, but gravitational waves are not light. They are space-time itself. Plasma is transparent to them. The universe has been transparent to gravitational waves since the first fraction of a second after the Big Bang. If we can detect and analyze the gravitational wave background with sufficient precision, if we can separate the contributions of primordial gravitational waves from those of black hole binaries, we could potentially peer through that plasma wall and see, in a manner of speaking, the very first moments of creation. We built a detector out of dead stars, and it may show us the birth of the universe. This is what neutron stars have given us. Not just astronomical curiosities, not just extreme physics, a tool, a window, a means of asking questions that we could not even properly formulate 50 years ago. Let's stay with that for a moment. It is worth pausing here, in the quiet, and truly letting this settle. Somewhere in the Milky Way, there are neutron stars that formed before our sun existed. There are pulsars that have been spinning, sweeping their beams across the galaxy for longer than Earth has been a planet. There are magnetars, neutron stars with magnetic fields so intense they would be lethal to any known form of biology at a distance of 1,000 kilometers, sleeping quietly in the galactic plane, occasionally rocked by starquakes that release, in a fraction of a second, more energy than our sun will radiate in its entire 10 billion year lifetime. There are neutron stars locked in binary orbits with other neutron stars, spiraling slowly toward each other, their gravitational waves already detectable, their eventual collision, a kilonova, generating enough energy to briefly outshine an entire galaxy and forge, in the collision, the heavy elements that no supernova can produce. Gold, platinum, uranium, the gold in your jewelry, if you wear any, the platinum in catalytic converters, the uranium in nuclear reactors, all of it forged in the collision of neutron stars scattered across space, incorporated eventually into planets, into oceans, into biology, into you. You contain atoms forged in the collision of dead stars. Every heavy element heavier than iron in your body carries this history. Every gold atom, every iodine atom, every traces of barium and strontium, all of it birthed in kilonovae, in the cataclysmic mergers of neutron stars across the billions of years of our galaxy's history. The universe is not simply a backdrop against which life occurs. The universe is the author of life's ingredients, and neutron stars are among its most prolific and violent workshops. And yet, and this is the thing that I find most quietly astonishing, for most of human history, we did not know they existed. The first pulsar was discovered in 1967 by accident. Jocelyn Bell, a graduate student at Cambridge, was working with a newly built radio telescope designed to study a completely different phenomenon. She noticed, in the data, a strange repeating signal. Regular pulses arriving every 1.3 seconds, so precisely timed that her first notes on the signal were labelled, half-jokingly, LGM1, for Little Green Men. The signal was, of course, a pulsar, the first pulsar ever detected, CP1919, and when the theoretical framework caught up, when it became clear that these objects were neutron stars, objects that had been predicted theoretically but never observed, the discovery reshaped astrophysics. Jocelyn Bell did not share in the Nobel Prize that was awarded for the discovery in 1974. The prize went to her supervisor and to another radio astronomer. This was a decision that has been criticized extensively by the scientific community in the decades since, and Bell herself has spoken about it with remarkable grace and equanimity. But the injustice of it does not diminish the discovery, and the discovery does not diminish her role in it. She found it. A young woman, working through reams of paper chart output by hand, noticed something that a less attentive mind would have passed over as noise. That is often how the universe reveals itself, not in a moment of dramatic revelation, but in a quiet anomaly noticed by someone paying careful attention. GPM J1839-10 was found the same way, in archival data, by people who decided to look more carefully at what was already there. Geminga was identified because someone wondered why a gamma-ray source had no visible counterpart and kept looking for 20 years. The gravitational wave background was detected because 68 pulsars were timed for 15 years by teams of astronomers working patiently, quietly, without knowing for certain that the signal was there to be found. Science, at its deepest, is an act of sustained attention, a willingness to keep looking even when nothing seems to be there, a commitment to asking the question again and again with better instruments and clearer methods and more carefully examined data. And what we find when we keep looking is always stranger and more beautiful than what we expected. There is one more thing I want to share before we close tonight. Something I find personally compelling about neutron stars, beyond all the physics, beyond the density and the gravity and the antimatter and the gravitational waves. It is this: a neutron star is what remains after catastrophe, after the violent death of something vast and ancient, a star that burned for millions or billions of years, that fused hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron, building the elements that make up the universe's chemistry step by step, generation by generation. And then, when it could fuse no further, collapsed under its own gravity in a fraction of a second. The outer layers exploded outward in a supernova so bright it briefly outshines the entire galaxy. And what remained, compressed, stabilized, spinning, is a neutron star. Not destruction, transformation. The star did not disappear. It became something new, something that cannot burn anymore, but can still sweep its beam across the galaxy for millions of years. Something that can collide with its companion and forge gold. Something that can time the arrival of gravitational waves and help us see the first moments of creation. Something that can, without intending anything, without any purpose or agency, bombard a planet 800 light-years away with antimatter for hundreds of thousands of years before the inhabitants of that planet develop the instruments to notice. The neutron star does not know it is remarkable, but we do. And that awareness, that capacity to look at a dead star spinning in the darkness and understand, even partially, what it is and what it means. That is one of the most extraordinary things about being alive. You are a temporary arrangement of atoms, sitting on a rock orbiting a star, looking out into a universe that has been operating for 13.8 billion years, and you are beginning to understand it. Not completely, not even mostly, but genuinely, rigorously, beautifully beginning to understand it. The 22-minute signal is still out there. GPM J1839-10 is pulsing right now as you listen to this once every 22 minutes from 18,000 light years away. We do not know what it is. We do not know what physics it is showing us that we do not yet have the framework to comprehend. Geminga is still racing through space at 210 kilometers per second, trailing its ghostly X-ray tails, flooding the surrounding light years with positrons that reach Earth and pass through everything on it. 68 pulsars are still being timed. The gravitational wave background is still accumulating in our detectors, slowly, patiently. Each year, adding more data. Each year, reducing the error bars. Each year, bringing us closer to a clear detection of the ripples from the beginning of time. And somewhere in the galactic plane, there may be dozens of objects like GPM J1839-10, pulsing away in data we have not yet fully examined. Waiting, patient as only the universe can be. The cosmos has been here for an almost incomprehensible span of time. It will be here long after every star we can see today has burned out, and it is full of things we do not yet understand. That is not frightening. That is an invitation, an open question that the universe has been asking since before life existed to hear it. What are we? What are you? We are, among other things, the universe's attempt to answer. If you found yourself genuinely curious tonight, if something in this exploration sparked a question you want to keep thinking about, I would love to know which moment surprised you the most. Was it the antimatter passing through your body right now? The 22-minute signal we cannot explain? The fact that your gold was forged in a neutron star collision? Leave it in the comments below. I read every single one, and your questions genuinely shape where this channel goes next. And if you're watching this at the end of a long day, or settling in for the night, or simply needed a moment of quiet wonder in a loud world, I'm glad you're here. The universe is vast and mostly empty, and also, somehow, full of exactly this kind of astonishment. Rest well. The pulsars will keep ticking while you sleep, but before you close your eyes, let me take you somewhere else, somewhere even stranger. Because we have talked about pulsars as objects that spin down, objects that lose energy, objects that travel a long, slow road from the frantic birth spin of hundreds of rotations per second, gradually slowing over millions of years toward the death valley where their beams go dark. But not all pulsars travel this road in the same direction. Some of them, improbably, spectacularly, spin back up. We call them millisecond pulsars, and they are, in a very real sense, the universe's most improbable recycling project. Here is how it works. A pulsar in a binary system, orbiting a companion star, will, over millions of years, slow down in the usual way. Its beam dims. It approaches the death valley. By all rights, it should be nearing the end of its active life, but its companion star has a different timeline. The companion, if it is the right kind of star, will eventually swell into a red giant as it exhausts its core hydrogen. And as it swells, some of its outer material will overflow the gravitational boundary between the two stars, what astronomers call the Roche lobe, and begin to stream across toward the neutron star. Matter falling onto a neutron star does not fall straight down. It cannot. The binary system is rotating, and so the infalling material carries angular momentum. It spirals inward, forming an accretion disk around the neutron star, a flat, hot, glowing ring of gas and plasma, growing hotter as it falls deeper into the neutron star's gravity well, eventually reaching temperatures of millions of degrees and glowing in X-rays. And as that matter falls and spirals, it delivers its angular momentum to the neutron star. It spins the neutron star up, gradually, over millions of years of accretion. Spin by spin, the neutron star accelerates. The dead clock is rewound. The old slow pulsar, approaching the Death Valley, is dragged back through the Death Valley, back through the region of fast-spinning neutron stars, past the speeds of typical pulsars, into entirely new territory, the fastest known millisecond pulsar, PSRJ 1748-2446 AD, completes 716 rotations every single second. Its surface, near the equator, is moving at roughly a quarter of the speed of light. A quarter of the speed of light, on the surface of a sphere 30 kilometers in diameter. And it is stable. Extraordinarily stable. The timing of millisecond pulsars is so precise that we use them for navigational purposes. Proposals have been made to use pulsar timing as a kind of cosmic GPS for deep space missions, where the known pulse arrival times of multiple millisecond pulsars could be used to determine a spacecraft's position in the galaxy to remarkable accuracy. Dead stars as navigation beacons, the universe providing infrastructure. Now, let's think about what happens when two neutron stars find each other. Binary neutron star systems exist. We know this because we have detected them. The first was discovered in 1974 by Russell Hulse and Joseph Taylor, who noticed that a pulsar was showing a regular variation in its pulse arrival times, a Doppler shift caused by the pulsar moving toward and away from Earth as it orbited an unseen companion. The companion, analysis showed, was another neutron star, and the orbit was shrinking. Hulse and Taylor measured the orbital period of the binary over years and found that it was decreasing. The two neutron stars were spiraling together. They were losing energy, and the energy they were losing was being carried away by gravitational waves, exactly as Einstein's general relativity predicted. This was the first indirect evidence that gravitational waves exist and carry energy. Hulse and Taylor won the Nobel Prize in 1993. The binary system they discovered, PSRB 1913 plus 16, will merge in approximately 300 million years. When it does, the collision will be spectacular beyond description. We have, in fact, already witnessed such a merger. On August 17, 2017, LIGO detected gravitational waves from the collision of two neutron stars. The event, EW170817. Unlike the black hole mergers LIGO had previously detected, this event also produced an electromagnetic counterpart, a kilonova, a burst of optical and infrared light visible to telescopes around the world. Within hours of the LIGO detection, dozens of observatories had trained their instruments on the source galaxy, watching the afterglow of the collision unfold in real time. The spectrum of that afterglow contained clear signatures of heavy elements being synthesized in the collision. Strontium was identified. The calculations suggested that the collision produced quantities of gold and other heavy elements on a scale measured in Earth masses. Multiple Earth masses of gold, forged in a fraction of a second, in the collision of two dead stars. The universe is profligate with its productions. It makes gold the way we make noise, as a byproduct of something else happening. GW170817 was not just a scientific milestone, it was a moment of profound synthesis. For the first time, a cosmic event was observed simultaneously in gravitational waves and light. the beginning of what astronomers call multi-messenger astronomy. The ability to observe the universe with not one sense, but two. To hear and see the same event. To cross-reference and correlate and build a fuller picture than either channel of information alone could provide. This is still new. This is still, by the standards of scientific history, the very beginning. The LIGO detectors are being upgraded. New detectors are being built, including LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave detector planned by the European Space Agency, with arm lengths not of 4 kilometers but of 2.5 million kilometers, capable of detecting the low-frequency gravitational waves that LIGO cannot hear, including, perhaps, the slow, years-long orbital dance of supermassive black hole binaries before their collision. And nanograv continues to time its pulsars. The picture being assembled, piece by piece, observation by observation, is unlike anything the astronomers of even 50 years ago could have imagined. Not just a catalogue of strange and extreme objects, but an integrated understanding of the universe's most energetic processes. The way stars die and leave behind engines of extraordinary physics. The way those engines pulse and spin and collide and forge elements and warp space-time. The way all of it, ultimately, feeds back into the next generation of stars and planets and, in at least one known case, living things sitting on a rocky world wondering where they came from. There is a concept in physics called ergodicity, the idea that a system, given enough time, will pass through every state available to it. The universe has had 13.8 billion years. It has been exploring its available states with tremendous thoroughness. And among the states it has explored, and continues to explore, are our neutron stars, objects at the absolute frontier of the possible. Objects that exist only because the laws of physics permit them to, and whose existence reveals those laws to us in ways that nothing else can. Every time we look more carefully at a neutron star, we learn something we did not know. Sometimes it confirms a prediction. Sometimes it contradicts one. Sometimes, as with GPM J1839-10, it presents something so strange that our existing frameworks simply do not have a category for it. That is not a failure of science. That is science working exactly as it should. The model is not the territory. The equations are not the universe. They are our best current attempt to describe it. And every time the universe shows us something our equations do not predict, we have been given an opportunity to make better equations. Neutron stars have given us general relativity tests. They have given us the first evidence of gravitational wave energy loss. They have given us gravitational waves themselves. They have given us the origin of heavy elements. They have given us the most precise natural clocks in existence. They have given us a potential window to the first moment of the Big Bang. And they have given us, in GPM J1839-10, a mystery so complete that we cannot yet even name what kind of thing is at its center. What will they give us next? That question does not have an answer yet. It will be answered not by prediction, but by observation. By someone, somewhere, reviewing data carefully, noticing something strange, and deciding to look more closely. Maybe that person is alive right now. Maybe they are a student. Maybe they are taking a night class in a small city somewhere, or reviewing archival data for a thesis, or running an automated signal search on a supercomputer that will flag something unexpected in its output at 3 a.m. while no one is watching. Maybe the next great discovery in a neutron star physics has already happened, and it is sitting in a file somewhere, waiting for the right person to open it. the universe does not announce its revelations. It embeds them in data, in signals, in the careful output of instruments pointed at the sky by curious creatures on a small planet. And it waits for us to notice. We are noticing. Slowly, carefully, one observation at a time. We are noticing. And every time we do, the universe we live in becomes simultaneously more comprehensible and more astonishing, more understood and more mysterious. The known expands, and with it, so does the boundary of the unknown. There is always more sky beyond the horizon. There will always be more sky beyond the horizon. This might be the most honest and most hopeful thing I can tell you about science. Not that it is converging on a final answer, but that it is always opening new questions. That every door we walk through leads to a corridor with more doors. That the universe is not a puzzle to be solved, but an exploration to be continued. And that human beings, improbable, temporary, made of the dust of dead stars, are exactly the right kind of creatures to continue it. You are here. You are curious. You are paying attention. That is enough. That is more than enough. That is, in the fullest sense of the word, remarkable. The 22-minute signal will pulse again in a few minutes, whether or not anyone on Earth is listening for it. Geminga will continue its race through the galaxy, trailing fire. The gravitational wave background will continue to wash through the pulsars of the Milky Way, leaving its subtle fingerprint in their timing. And somewhere, in the archive of some radio telescope, there may be a signal no one has yet recognized. Patient, stable, strange, waiting for someone to look carefully enough to see it. The universe is not finished surprising us. It is only just beginning. And before you drift off tonight, I want to leave you with one final question. The one that I think is the most interesting of all the questions raised by tonight's exploration. GPM J1839-10, the 22-minute signal, the object that sits below the Death Valley of pulsars, that produces no X-ray emission, that has been pulsing with impossible stability for at least 35 years. That does not fit any category we have. What do you think it is? Not what the science says. We've covered that. I mean, what does your intuition say? What does it feel like when you sit with the mystery of it? An exotic neutron star in a configuration we haven't modeled yet. Something genuinely new? Something that will require us to revise our understanding of how matter behaves at extreme densities? The comments below are a place for that kind of wondering. Real wondering. The kind that doesn't need to be correct to be valuable. The kind that sometimes points in the direction of something true before the equations catch up. I'll be there reading. The conversation is one of my favorite parts of this. Thank you for spending this time in the deep end of the universe. Thank you for being curious. Thank you for being the kind of person who finds dead stars beautiful. Rest well tonight. You have earned it. The pulsars are keeping time. The cosmos is doing what it does. And tomorrow, there will be more to learn. There is always more to learn. Let me take you back to the beginning of this story. Not the beginning of tonight's video. The beginning of neutron stars themselves. To understand what a neutron star truly is, you need to understand what came before it. Because every neutron star was once something else, something vast and luminous and alive, in the way that stars are alive. Not with biology, but with process, with the continuous self-sustaining nuclear fire that we call fusion. Stars are, at their core, a negotiation between two forces. Gravity, which wants to collapse everything inward, and the outward pressure of radiation produced by fusion, which resists that collapse, A star exists in a state of balance between these forces, not a static balance, but a dynamic one. The interior is in constant motion. Convection currents carry hot plasma upward and cooler plasma downward. The rate of fusion adjusts to the pressure. The balance is maintained for millions or billions of years, but the balance cannot last forever. Fusion proceeds through a sequence of stages, each one producing elements heavier than the last and releasing progressively less energy per reaction. Hydrogen fuses to helium. When the hydrogen in the core is exhausted, the core contracts under gravity until the temperature is high enough to fuse helium to carbon. When the helium is exhausted, the carbon fuses, then oxygen, then neon, then silicon. Each stage is shorter than the last because the reactions are less efficient and the star must burn faster to maintain its pressure against gravity. The final stage, silicon fusion, which produces iron, lasts only a few days in the most massive stars. Iron is the end of the road. Iron is the most stable nucleus in the periodic table. Fusing iron does not release energy, it absorbs it. When a massive star's core fills with iron, it has nothing left to burn. The outward pressure drops, gravity, which has been waiting for this moment for millions of years, wins instantly. The iron core, which contains roughly the mass of our Sun, compressed into a sphere a few thousand kilometers across, collapses. In a fraction of a second, less than a quarter of a second, it contracts to a sphere 20 kilometers in diameter. The density exceeds that of atomic nuclei. Protons and electrons are forced together, producing neutrons and neutrinos. An almost incomprehensible flood of neutrinos, more energy in that instant than our Sun will radiate across its entire lifetime, pours outward. The infalling outer layers of the star slam into the newly formed neutron star and bounce. A shock wave propagates outward. The neutrinos carry energy into the shock, amplifying it. Within hours, the outer layers of the star, billions of kilometers of stellar material, are expelled outward at a significant fraction of the speed of light. This is a supernova. What remains behind is the neutron star, the compressed core. The most extreme ordinary object the universe can make without crossing the threshold into a black hole. From the outside, looking at the location of a star that has just gone supernova, you would see a brightening, an explosion of light so intense that a supernova in our galaxy could be visible in daylight. Historical records contain accounts of supernova bright enough to see with the naked eye in the middle of the day. The supernova of 1054, which produced what we now call the Crab Nebula and its central pulsar, was recorded by Chinese and Arab astronomers and was reportedly visible in daylight for weeks. But the neutron star itself is invisible to the naked eye. Its surface glows in X-rays and gamma rays. Its radio beams, if they happen to sweep across Earth, are detectable only with radio telescopes. It is there, enormously dense, rapidly spinning, generating a magnetic field of extraordinary strength, and it is, to unaided human vision, nothing. This is a consistent feature of neutron stars that I find quietly remarkable. They are among the most extreme objects in the universe, and they are largely invisible to us. We see the Crab Nebula, the vast glowing remnant of the explosion, but the pulsar at its center is a faint point requiring instruments to detect. We detect the gravitational waves from neutron star mergers, ripples in space-time itself, but we cannot see the neutron stars producing them until after they collide and produce a kilonova. The most extreme things in the universe are often the hardest to see. That is a metaphor I will leave you to apply as you see fit. the Crab pulsar is worth dwelling on for a moment. It is one of the best studied neutron stars we know, and it is located relatively close to us, about 6,500 light-years away. It spins 30 times per second. It was formed in the supernova of 1054, which makes it not quite 1,000 years old, a child by neutron star standards. And it is slowing down measurably. Its spin-down rate is well characterized. It powers the Crab Nebula with its wind of particles and radiation, causing the nebula to glow with extraordinary brightness across the electromagnetic spectrum. The Crab pulsar is also responsible for one of the most significant observations in pulsar history. In 1969, it was detected producing optical pulses of visible light, confirming for the first time that pulsar signals were indeed produced by rotating neutron stars rather than some other mechanism. Seeing a neutron star wink at you in visible light 30 times a second is about as direct a confirmation as physics gets. But even the Crab, well studied, nearby, decades of observation, still holds surprises. It undergoes what are called glitches, sudden, discontinuous increases in its rotation rate, not by much, fractions of a millionth of a rotation per second, but enough to be measurably, unambiguously detected. The glitches happen unpredictably and are followed by a slow relaxation back toward the expected spin-down rate over weeks or months. What causes glitches? We are not entirely certain. The leading hypothesis involves superfluid vortices in the interior of the neutron star, regions where neutrons form a quantum superfluid, a state of matter with zero viscosity, and rotate collectively in quantized vortex lines. As the outer crust of the neutron star slows down due to magnetic braking, the superfluid interior continues at a higher angular velocity. Periodically, the vortices move outward, transferring angular momentum from the fast-spinning interior to the slower-spinning crust, causing the sudden spin-up we observe as a glitch. This is not speculation. This is the leading scientific model, based on decades of observation and theoretical work. And what it implies is extraordinary. The interior of a neutron star, this object smaller than a city, made entirely of neutrons, with gravity 200 billion times that of Earth, contains a quantum superfluid, a state of matter that exists nowhere else in the universe at this scale. A state of matter we can only produce in laboratories at temperatures near absolute zero, occupying a microscopic volume, existing there as a scientific curiosity. In a neutron star, it may fill an interior volume of thousands of cubic kilometers. The interior of a neutron star is, in some ways, the most exotic laboratory in the universe. We cannot reach it. We cannot sample it. We can only infer its properties from observations of the surface and from the behavior of pulsar timing data. But those inferences have led us to conclude that matter can exist in states that simply do not have any parallel in ordinary experience. Right now, as you watch this, something invisible is passing through your body. Not a thought, not air, not light, antimatter. Tiny particles of it, the rarest, most exotic substance in the known universe, are colliding with the atoms inside you at this very moment. They have been doing this your entire life. They did it while you slept last night. They did it the moment you were born. They did it long before humans walked this planet. And for most of history, we had no idea. We didn't know where these particles were coming from. We didn't know what was making them. We pointed our telescopes at every corner of the sky and found nothing that could explain it. For decades, some physicists quietly wondered if the answer was something we had never encountered before, something that would rewrite our understanding of matter itself. The answer, when it finally came, was somehow more astonishing than anything they had imagined. It was a dead star. A dead star, 800 light-years away, spinning 4 times every second, trailing ghostly X-ray tails across 3 trillion kilometers of space. And it had been bombarding our planet with antimatter for longer than our species has existed. Silently, invisibly, relentlessly. And that star, that extraordinary, violent, beautiful, almost incomprehensible object, is just one of a kind. Just one example of what may be the strangest category of object in the entire observable universe. Tonight, we are going to follow the evidence into the deep unknown. We are going to cross into a realm where matter behaves in ways that have no parallel in ordinary experience, where a single teaspoon of material outweighs every human being who has ever lived, where the surface of an object the size of a city generates gravity so extreme that if you fell from just 1 meter above it, you would hit the ground moving at 1,500 kilometers per second. We are going to talk about neutron stars, and I promise you, by the time we are done, you will never look at the night sky the same way again. Take a breath, get comfortable, let your mind open, because the universe is about to show you something extraordinary. Let's begin somewhere quiet, somewhere that feels, at first, almost ordinary. Imagine you are standing outside on a clear night, far from any city, far from any artificial light. The sky above you is the deepest black you have ever seen, and it is absolutely filled with stars. Thousands of them, tens of thousands. So many that the individual points of light begin to blur into a soft, luminous band stretching from one horizon to the other. The Milky Way, our galaxy, seen from the inside. Now, somewhere in that band of light, in a region of the sky we call the Gemini constellation, there is something you cannot see. Not because it's too small, not because it's too dim, but because it is operating at a frequency your eyes were never built to detect. It is pulsing with gamma radiation and X-rays, sending waves of high-energy light across the 800 light-years between us with a rhythm as steady as a heartbeat, once every 0.237 seconds, 4 times every second. It has been doing this since long before the Roman Empire fell, long before the pyramids were built, long before the first modern humans crossed out of Africa. We named it Geminga. The name is a small, quiet piece of poetry. It combines the constellation where it lives with the type of radiation it emits. But in the Milanese dialect of Italian, it also means something else entirely. It means it's not there, and for a long time, that is exactly what it seemed like. A source with no visible origin. Radiation arriving from a point in space that appeared, to every instrument we had, to be completely empty. Geminga was first detected in 1972. For nearly 2 decades after that, we had no idea what it was. That is where we begin. But to understand why Geminga is so strange, and why it matters so deeply to the story of the antimatter raining down through your body tonight, we first need to understand what neutron stars actually are, because most people have heard the name. Very few people truly feel what these objects mean. So let's take a moment. Let's really sit with this. Every atom in your body, every atom in this planet, in every planet, in every star you have ever looked at, is almost entirely empty space. The nucleus of an atom, where virtually all of its mass is concentrated, is vanishingly small compared to the total size of the atom. If you were to magnify a single hydrogen atom until its nucleus was the size of a marble, the outer edge of the atom's electron cloud would be somewhere around the length of a football field away. That is how much empty space exists inside ordinary matter. That is how hollow everything around you truly is.